In an amazing turn of events, I remembered that I'm supposed to do chapter 18, section 4, problem 6 before I started talking about flux integrals. And so here is chapter 18, section 4, question 6. L is the line segment from 0, 0 to 2, 2. And the vector field is 3x minus y times I plus x times j. The point of this problem is to not just calculate this line segment, but to calculate this line segment with two different parameterizations of L. So we know some things. If F is a gradient field, then the gradient fields are path independent, and all that matters are the endpoints of the curve. So if F is a gradient field, then the path is then F is path independent. If F is a gradient field, then F is path independent, and all that would matter are the endpoints. But if F is not a gradient field, then the path matters. So then one level above, if F is not a gradient field, then the path matters. How we get from point A to, or point P to point Q, that's what they were using. How we get from point P to point Q is of significance. So then we need to parameterize the curve. So that is in the case where we are parameterizing the curve, we have seen that there are many ways to parameterize a curve from one point to the next, even the same path, many ways to parameterize the same curve from one point to the next. So this problem is raising the question, does the parameterization matter in this calculation? So this question So problem 6 is asking, does the parameterization matter? It doesn't truly address that. It just gives you 2 for one particular instance. But these are the things that we want to think about when we're looking at this problem. We don't want to just take this problem into a vacuum and deal with that. Question? I see a raised hand. Is there a question? All right. So let's take a look at the parameterizations. So we have this, I was just pointing with the cursor and you can't see that part. So we have this vector field and the curve is a line segment from 0, 0 to 2, 2. So our L here's X and Y goes from 0, 0 to 2, 2. So there's our line segment L. The only things that have to happen are that we start at 0, 0 end at 2, 2, and go in one direction, go from 0, 0 to 2, 2, and then that's it. And not go the other direction, maybe not go back and forth as we go up there, just from 0, 0 to 2, 2. So they suggest a couple of parameterizations. One of the parameterizations, B of t is 2t and 2t. So one of the parameterizations, B of t is 2ti plus 2t times j, and this is for t between 0 and 1. So we should make sure that this parameterization does what we intend it to do. When t is equal to 0, if t is equal to 0, then b of t, or b of 0, is 0i plus 0j. So we're starting at the right place. And when t is equal to 1, then b of 1 is 2i plus 2j. So we end at 2, 2. So that's good. This is as advertised. We're going to start off at 0, 0, and we can watch t increase from 0 to 1 and end up at 2, 2. All we're doing is we're looking at the line y equals x. So all we really need out of our parameterization is that the x and y be the same. That's really what's going on here. So for this line segment, the defining characteristic of this line segment is it's along the line y equals x. So we should see x and y be equal. That's what we're looking for. Any questions? If I change these two t's to 0.2t, 0.2t, and 0.2t, and then I could just run t from 0 to 10, and I would accomplish the same thing. So it could be that some outside influence says, I don't want to do this in 1 unit. I want to break it into 10 units. It's going to take 10 t units to go from 0.00 to 0.22. I can go t goes from 0 to 10 just with 0.2t and 0.2t. I just need the x's and y's to be the same. I need to start at 0, 0 and end at 2, 2, and possibly not just turn around in the middle and go back and forth. All right. So let's calculate this line integral. We've got our parameterization b of t. Oh, I was using b of t for the direction. Uh-oh. So here's our b of t. This is taking the place of r. So if I look at the dr, it's going to be the derivative. So it's going to be 2i plus 2j dt. So now I have dr. I need to evaluate my vector field at this parameterization. So my line integral will look like the integral from 0 to 1 of 3x minus y. So 3 times 2t minus y, which is also 2t. Parentheses, okay. Plus x, which is 2t, times j. This is my vector field evaluated. 1, 2. This is the vector field evaluated at the parameterization, and I find the dot product of this f at b of t in this case dot 2i plus 2j dt. So this is the integral that we're calculating. We've gone from our line integral with all the vectors, and now we're just looking at a single variable integral in t. probably stand to clean this up a little bit. So we've got 6t minus 2t is going to be 4t plus 2tj, and then we're going to dot product 2i and 2j. So when we find the dot product, we'll have 2 times 4 is 8t plus 4t. And then we'll integrate this from 0 to 1 dt. Any questions? So the integral of 12t is going to be 6t squared, evaluated from 0 to 1, so 6. All that for 6. Now we want to use another, this problem is from 4. Now we want to use a different parameterization from 0, 0 to 2, 2. So let's check that one out. Let's look at a different parameterization from 0, 0 to 2, 2. Once again, we're along the line x equals y, or y equals x. And we want to make sure we go from 0, 0 to 2, 2. And here we have we're suggested a different parameterization. So in this case, c of t is going to be t squared minus 4 over 6. So t squared minus 4 over 6 times I plus t squared minus 4 over 6 times j. We should check, does this go from 0, 0 to 2, 2? So c of 0 is going to be oh, we're not going from 0, 0. Excuse me. So we're using this parameterization from 2 to 4. So in this case, t is running from 2 to 4. This is just an alternate parameterization. It has one of the things that we know we should be looking for, that x and y will give us the same values so that we will stay on the line y equals x. We should make sure that the endpoints are going to match up. If I evaluate this c at 0, I don't want to do 0. I just got through saying that we're going from 2 to 4. T equals 2. So we get 4 squared minus 4 over 0, over 6, which is 0. And 4 squared minus 4 is also 0. So correct starting point. And then when t is equal to 4, we get 4 squared minus 4 over 6. And the same thing, 4 squared minus 4 over 6j. 4 squared is 16, minus 4 is 12, over 6 is 2. So we get 2i plus 2j. So we got the correct end at 2, 2. So you go from 0, 0, and start at 0, 0, and end at 2, 2. So we're going in the right direction. Our dr is just going to be the derivative of each of these terms. So we got t squared over 6. The rest is a constant, minus 4/6. So this is going to be 1/6 times t squared minus 2/3. So I need the derivative of this term. That's going to be 1/3 t times I plus 1/3 t times j, all times dt. Then we just need to set up our line integral. In this case, our line integral will go from 2, our integral will go from 2 to 4, and I'll have the function evaluated at the parameterization. So the function is 3x minus y. So I'll have 3 times x minus y plus x times j and this is dot 1/3 ti plus 1/3 tj dt. Look at all the space up here that I could have saved for over here. This is like the parking conundrum. It's like there's a space that will clearly fit 3 cars, but the cars didn't line up right at the front of the space, like along the street, like parallel along the street. But they didn't think, they didn't plan ahead. 3 cars would fit there if we had just planned ahead and got along. But we didn't, so I have these massive gaps over here, and then just everything's just crammed together over here. None of that's that important. What we need to do is simplify all this craziness. Over here, we've got 3 of these things minus 1 of these things, so we've got 2 of these things. So really what we're looking at in this, the I component here is, let's see, 3 minus 1 is 2, divided by 6 is 1/3, so we got 1/3 t squared minus 4. 1/3 of a t squared minus 4 times I. And then we need to calculate the dot product. So we're still going to integrate from 2 to 4. And we'll have the I times the I. So we'll have 1/9 t times t squared minus 4. That's from multiplying the i's. And then if we multiply the j's, we'll have 1/3. 1/3 times the 6 is an 18th. T times t squared minus 4 dt. So dr is just going to be, actually I should have called it dc. It's just the derivative of the the parameterization. So this is just the parameterization of c. So maybe I should have called it dc. And I wrote the t squared minus 4 over 6 as a 6th t squared minus 2/3. So it'd be easier to take the derivative. So that's why I got the 1/3 t plus I plus 1/3 tj. So all this works out to 1/6 t times t squared minus 4. So we could do this with substitution, or we could multiply this whole thing out. Too many choices. The idea is that we'll work this out and we'll come up with 6, hopefully. Any questions? So it's important to remember what the overarching point of this problem was. It's to look at 2 different parameterizations of the line segment from 0, 0 to 2, 2. Recognize that our vector field is not a gradient field, so the path matters. Knowing that there's a lot of ways we can parameterize a path, does the parameterization matter? This problem is suggesting that the parameterization doesn't matter. So going back to what we care about in this particular problem, So this problem is suggesting that the parameterization doesn't matter. This problem is suggesting that the parameterization doesn't matter. As long as the parameterization does report the correct set of points, it doesn't matter how we get from point P to point Q, as long as we follow the correct path. It doesn't matter how we describe that path. So that's an important thing to recognize. Any questions? In both of these paths, if we look at t squared minus 4 over 6, that's a parabola from 2 to 4. That particular function goes directly from 0, 0 to 2, 2. So what would be interesting, what if the path didn't just go directly from 0, 0 to 2, 2? What if the path went from 0, 0 to 1, 1, then back to 0, 0, and then up to 2, 2? What if it went back and forth? So what if, for example, we know we stay along the line if our x and y coordinates are the same. We know that that would keep all those points on that line. But what if instead of using a line, 2t, or a parabola, t squared minus 4, a parabola past its vertex, what if we parameterized the curve with something like cosine from 0 to 2, so say 0 to pi, now 0 to 2 pi. What if it goes back and forth? Or maybe 0 to 3 pi, so it goes up, down, and up again. What if we did that? Would that affect things? So that's an interesting question to think about. The question is about whether the parameterization matters. And both of the parameterization, we go directly from 0, 0 to 2, 2 in one direction. What if our parameterization doubled back on itself? Ultimately went from 0, 0 to 2, 2, but it started off at 0, 0, went up a little bit, and then back, and then continued on to 2, 2. What if our path is indecisive? We should go. Now let's go back. Now let's go. What if we built a path that did that? Or just went from 0, 0 to 2, 2 a couple of times? Or even just went from 0, 0 to 2, 2. It just went there, and then went back again, and then went there. We just have excessive path. Maybe if our path is indecisive or our path is just excessive. Imagine like with a cosine where it goes down, up, and then down again. So instead of cosine going from 0, 0 to 2, 2, oh, I'd have to adjust these somehow. Can't just do that. It won't end up at the right spots. Instead, I have to go to 2, 2, so, and I have to start off at 0. I could use a sine, something sinusoidal. From 0, and t goes from 0 to not to pi, or 3 pi. Something that'll go up, down, and up again. That would be an interesting question to explore by actually building that parameterization and then seeing what happens. So what about the parameterization will change things? That's my question. The problem is suggesting that the parameterization doesn't matter. But what if our parameterization is overly complicated? I guess that's the question I want to ask. Let's pause the video here and talk about other problems.